Right, ladies and gents, thank you for joining us for this special Monday Geotalk. We don't normally have Geotalks on a Monday, but today we have a special guest who's flying back to Europe this evening, and that is Nick Arndt. Nick, thank you for joining us at the end of what is probably a long field trip. For those of you who don't know Nick, he hails from Australia, for which we all forgive him, where he did most of his undergrad education, one of his MSc at the Australian National University. And he went overseas to Canada to do his PhD, and then did several postdocs in North America, and spent most of his career thereafter working in Europe. I think for the longest time at Granite University, where he's now an emeritus professor. He's also worked in industry in several different environments, most recently in a seismic consulting company. But as you'll see from the talk tonight, he's mainly a petrologist and a geochemist. So I'm sure that company has benefited from a lot of petrological and geochemical advice. And he's the author of two very good books, one on komatiites and the other on metals and society. But tonight you can see the title of his talk. And Nick, over to you. Thank you very much.
Well, thanks, Grant. Normally, I would start a talk like this by thanking Arndt for inviting me here to give the talk, but in fact, I invited myself. I sent a message to Lou, we passed it on to Grant and said, because I was reading yet another paper in which the authors said, in the first part of Earth history, through to the end of the Archean, the Earth behaved differently. There was no plate tectonics. There are various other processes which I'll talk about. And I said, no, I don't think the Earth operated that way. The point I'll be trying to make is that throughout most of Earth history, at least back to 3.8 billion years, or maybe even earlier, some form of plate tectonics operated. And this is what I'll try to get across to you. But I'm also I like democratic science. So I'm going to start with a poll of you. Can we just have the next slide?
Yeah. I'm just going to put the microphone a bit closer. Maybe if you can just speak a bit louder. And I'll get you the next slide. Hopefully. There we go.
There we go. So in this slide, we see a question. A question I asked myself when I read this paper. Why do so many geoscientists believe that Archean geodynamics was very different from modern geodynamics? Many people, you find many papers who said early in Earth history was the Earth operated like this, with what's called a stagnant lid, some sort of continuous crust lithosphere of mafic composition that covered most of the Earth. There were large mantle plumes. There was a process called Sagduction, in which portions of this crust sagged down back into the mantle, a process that is very different from modern plate tectonics. So we have two basic schools. One, and I'm part of that school, which thinks that some form of plate tectonics operated. And another school who thinks, no, it was different. There were other processes which transferred material from the surface deep back into the mantle. So I'm going to start with my poll. I want you to, as a show of hands, indicate on one hand whether you thought plate tectonics operated from about 4 billion years, or on the other hand, that there was some other process, stagnant lid, something like that. So first question, who is in favor of something different, stagnant lid? And you have to show me your hands. 1, 2, 3, 4, 5, 6, 7. And who is in favor of plate tectonics from about 3.8? 1, 2, 3, 4. So, hey, you can't vote twice, did you? No, okay. Okay, so that's interesting. So roughly 50-50, which I think is in the middle. You're in the middle. Oh, as always, right? Yeah. Okay, now maybe I'll ask the same question later at the end of my talk. But this is what I'm going to talk about. Oops. So the same question. So where does this idea come from? It's been around a long time. There was some sort of stagnant lid, Sagduction, and so on. And a lot of the ideas come from the people who study other planets, because Venus, a planet very similar to the Earth, does seem to have had a stagnant lid, some sort of mafic, immobile crust at the surface. And there's some evidence that plumes still operate on Venus. And this idea has been translated to the Sagduction models for the Earth. But so what is the evidence? What are the arguments that are advanced to say that there was no plate tectonics early on and that some other process operated? There's a line of geological arguments, as we see here. For example, Bob Stern, this is a paper from Bob Stern, who said a lot of the features of modern plate tectonics are not found when we look at the oldest rocks. For example, we see no ophiolites, very few alkali volcanics, no kimberlites, no blue schists, and so on. Now, this observation is probably valid, but I think this can be immediately explained because, for reasons I'll talk about later, the mantle was hotter in the Archean. The mantle was hotter. The crust was hotter. If the mantle was hotter, there was no low-degree melts like kimberlites and alkali volcanics, probably no real ophiolites because the oceanic crust was thicker. I think these sort of geological arguments don't hold much weight. But there's another series of arguments that are illustrated here. And here, for example, Sharon Richardson said that if you look at inclusions in diamonds, there are no eclogitic diamonds older than about 3 billion years. If you look at large sets of data, such as shown here, there seems to be some sort of break at around 3 billion years, 2.5, 3 billion years. And here another diagram, this is from Bruno Duin, who said something seems to be happening in a lot of different indices around 3 billion years. And if we just do a zoom on this point here, he said these breaks in the rate of crust formation or various other things separates the modern Earth, the situation in the modern Earth when there was subduction, from a pre-subduction regime. Behind a lot of these arguments is reasonable inferences that the mantle was much hotter, significantly hotter in the Archean, in the early Archean. This is reasonable because there was still heat escaping from the core. The radioactive heating within the mantle was much greater. There are some theoretical arguments to say the mantle was hotter in the Archean. And we find approaches like this from Claude Hertzberg and colleagues who used the compositions of basalts in greenstone belts to estimate the potential temperature being the temperature of the source of these basalts. And we see today the potential temperature is around 1350. In the Archean, these black dots, the red dots are komatiites. They were hotter. They come from hot plumes. But these black dots, which are called non-arc basalts, represent the composition of the ambient mantle. And you can see there's maybe 250 degrees difference. The Archean mantle may have been 250 degrees hotter than the modern mantle. Now, this is important because it provides the basis for a lot of numerical modeling by the Van Hunen group in Durham or the Tereskaya group in Zurich. They run numerical models trying to show how subduction would operate in a hotter Earth, whether subduction is possible if the mantle was much hotter, which would mean the lithosphere is less rigid. So if you look at this type of modeling here, when we see delta T, which is the difference between present-day mantle temperatures and Archean, mantle temperatures. We see in this model that subduction seems to work quite well nowadays. They can model modern subduction, which is good. But if the temperature gets more than about 200 degrees hotter, subduction becomes intermittent, and the slab breaks up very soon. Here's another set of models from the Tereskaya group in Zurich, who started off with a situation like this: peridotite, a layer of basalt, dry at the bottom, hydrated at the top. And if they run their models, they see that the base of this thick upper layer of basalt becomes unstable, and it drips down into the underlying mantle, a process that people have been calling sagduction. Sagduction being the idea that the base of a thick pile of basaltic material will become unstable, and blobs or drips of this material will move down into the mantle. This is the idea that you find in many papers, the idea that in the Archean, throughout the early part of the Archean, circulation material from the surface to the interior of the mantle was conducted by this sort of process. So here we see the two models. On the left, a stagnant lid sagduction model, continuous crust, with portions of this thick crust sagging down into the lithosphere. And here's the modern process. And here, essentially the same idea. Subduction as opposed to sagduction. Now, this is the background. But I ask myself, is there any valid reason to believe that plate tectonics did not operate in the Archean? We know the mantle was hotter, and this might have an influence. We'll talk about that later. But there's another important parameter, another feature that distinguishes Venus, where we did seem to have had a stagnant lid regime, from the Earth. And that important difference is water. It's a paper written by Ian Campbell and Ross Taylor, 1983, with the title, No Water, No Granites, No Oceans, No Continents. And so basically, if you follow this line of reasoning, if there was water, there's probably continental crust. And I'll point out that continents, the formation of continents is an important part of this whole argument. We know from studies of the zircons from Jack Hills in Australia, here's a paper by Mojis et al., that oxygen isotopes indicate relatively low temperatures in the sources of these zircons, which almost certainly means the presence of water. So all the ingredients for plate tectonics, in my opinion, oceans, hot convecting mantle were present from at least 4.3 billion years ago. Why shouldn't there be plate tectonics? So I'm going to explore this issue, focusing on the granites, because I think they're the key to the whole issue. I'm going to ask this question, same one I asked at the start. When did plate tectonics start? When did subduction become the main granite-forming process? I'll be talking about the mechanism of continental crustal growth, whether it's related to subduction or plume-related processes, sagduction. And then I'll talk a little bit about the rate of growth and the tempo of growth. I'll insist on the fact that a key element of global tectonics, global geodynamics, is the formation, the growth of continental crust. And essentially, the growth of continental crust, if we consider it from a petrological or a geochemical basis, is the formation of granitic magma. And I'll show these two diagrams to say continental crust consists in large part of granitic material. Growth of continental crust represents the formation of granitic material, separation of material, granitic composition from the mantle. And I show this diagram. It's my recipe for granite. You need a basaltic starting material, heat, water, and you get granite. But I emphasize that the basaltic starting material can be solid basalt, for example, in a subducting slab, which could partially melt. But more commonly, the starting material of basaltic composition is mafic magma, as in the modern subduction zone. So the slab subducts, it dehydrates, water causes melting in the mantle wedge. This hydrous basaltic magma enters the base of the crust where it undergoes this mash process, mixing, assimilation, storage, high homogenization, to eventually produce the more evolved granitic material that ascends to higher levels in the crust. So that's an important constraint. We need to find a mechanism for forming granitic magmas. Another important constraint is the geochemical signature of granitic rocks, which look like this: a trace element diagram, mantle normalized trace element diagrams, in which we see what we call the anomalies, a negative Nogan tantal anomaly, a positive lead anomaly, and so on. These are the signatures of magmas that form in modern-day island arcs, as shown here. This is a paper from Marlene Edelberg, showing a typical arc basalt from Santorini with these negative Nogan tantal anomalies and positive lead anomalies. We have to explain that. So we know material of granitic composition can form in subduction zones. This is what's happening now. But this is not the mechanism that is advocated by those people who talk about a stagnant lid. For them, the granitic magmas, which form the granitic crust in the Archean, formed by a different process. This is a diagram from a paper by Jean Bédard, who's one of the main advocates of this process, who envisages a thick pile of basaltic material at the surface of the earth. This thick part, the lower part of this thick pile of basaltic material converts to eclogite, which is dense, which moves down into the mantle where it undergoes melting to produce granitic magma. Now, in my opinion, Sagduction models, this type of model in which the lower part of a basaltic layer sags down to form granitic magma, doesn't work. This is the process that's advocated, for example, in all the models I showed you earlier by the Tereskaya group. I do not think this model works for two reasons. The first is that any thick pile of material of mafic composition, whether it's lava flows, a thick pile of lava flows, an oceanic plateau, bushveld, does not have a uniform composition from top to base. Thick piles of basaltic material differentiate with basaltic material at the top and ultramafic cumulates at the base. And the lower parts of these thick piles are not hydrated, they're dry. So here's just some examples of what we see in the geological record. A thin komatiite flow, the upper part is spinifex, the lower part is olivine cumulate. The bushveld, more evolved rocks at the top, lower rocks at the base. And here's the Yontong Java Plateau, 40 kilometers of material of essentially mafic material. The basalt's at the top, the upper minerals are basalt and gabbro. The lower part is ultramafic cumulates. This is what happens, but why does it happen? So why does a thick pile of mafic material differentiate? There are two main processes. If to form a thick pile of basaltic material, the melting must take place deeper in the mantle. Now we know when melting takes place at several tens of kilometers in the mantle, the melt does not have a basaltic composition. It has a more magnesian picritic composition. So the primary magma that comes from deep down, melting the mantle, has a picritic composition. The erupted material has basaltic composition, 5 to 7% MgO compared with 15 to 20. The difference is explained by the accumulation of pyroxene and olivine as cumulates in the lower part of the crust. And there's another complementary process. We know that in any eruptive setting, whether it's the Andes or an oceanic crust or an oceanic plateau, only a small fraction of the magma produced in the mantle erupts, and a larger proportion is trapped in the crust as intrusions. The dense picritic magma tends to be trapped low down where it crystallizes to olivine. The less dense evolved material ascends to the surface. So instead of having this situation when the lower part of this basaltic pile converts to eclogite, this doesn't work because the lower part is not basalt, it's ultramafic cumulate. A thick differentiated pile of basaltic magma would look something like this, with olivine cumulates relatively dense at the base, a little bit more iron-rich than the underlying asthenosphere, but differentiation. The water is confined to the uppermost layers. The uppermost basalts will interact with seawater and become hydrated. But the lower portions will contain little water. So if we want to model sagduction, we have to ask ourselves the question, could this basaltic material, hydrated basalt, the material that is necessary, the necessary starting point for the formation of granite, be dragged down deep into the mantle, whether it could undergo partial melting? Now, I did some studies with Alberto Roma, who is a PhD student in Paris, because I drew this diagram simply as a cartoon. We wanted to test this with numerical modeling, which is what he did. He started off with a model like this, the mantle, crust, which is differentiated, lower cumulates, upper basalts. He did numerical models, which are shown here, the crust, upper crust basalt, lower crust cumulates, the mantle. He modeled what would happen in time, and in this curve we have time and depth, dimensionless. This curve represents what happens to the lower ultramafic cumulates, which could sag down into the mantle. They go down deeper and deeper down to the mantle. For a while, they drag down a portion of the crust, but then there's decoupling, and the upper crustal layers remain in place. Any reasonable modeling of sagduction with reasonable starting compositions doesn't drag the hydrated basalt deep into the mantle. Granitic melt is not created in drips. Hydrated basalt is not dragged deep down to the mantle. Even if this were to work under special circumstances, the water that is released moves upwards into cooler rocks. This is not a situation in which you can cause partial melting to produce granitoid magmas. And here to emphasize, the continental crust is made up mainly of granites. These are my main arguments for saying that this process doesn't work. A viable process, the only viable process for producing granitic magmas, which is the component of continental crust, is subduction. Subduction, which is the ideal situation to form granitoid magmas. What do we have here? We have the oceanic crust being hydrated at the ocean ridge or during bending. Dehydration releases water into the mantle wedge, which is hotter. This addition of water causes fluxus melting to produce hydrous, picritic, or basaltic magmas, which go to the base of the crust, differentiate to form the granitic magmas. So what I've shown you so far, I hope, is that the sagduction models don't work. They're not a viable process for producing granitoid magmas. But we had this problem that, according to the modeling that had been done, subduction is intermittent or impossible if mantle temperatures are too high. The way around this enigma is one solution, perhaps the mantle was not as hot as estimated by Lord Hertzberg. So more recently, Jerome Gunn and other co-authors have re-looked at the data, and they come up with these red dots here, which represent the temperature of the mantle, and they get temperatures that are not nearly so high. And there's a number of other arguments along this basis. Perhaps the ambient mantle in the Archean was not as hot as was estimated. So perhaps that's the explanation. But more recently, there's a very interesting paper written by Jan Koranaga, 2021, in which he analyzes in detail the various models that have been done. And he makes a very important point. For models like this is Tereskaya groups, or Van Hunen's models, they assume a weak lithosphere. They assume that the lithosphere was weak because it was hot. Koranaga says, no, perhaps this is not correct. Oh, sorry, in Tereskaya, they assume a melt-bearing peridotite, which is also weak. Koranaga says this is not correct. The mantle, the lithosphere, was certainly hotter, but it was dry. His argument is that in the Archean, the mantle was somewhat hotter, but if it's hotter, it's less capable of containing water. So in his opinion, most models assume weak lithosphere because of melt of water. Dry solid peridotite is much stronger, and in his models, subduction is possible. So, how's it going? Yeah. So the conclusions of the first part. This is the first part of my talk. In my opinion, subduction is the only plausible way of producing granitic magma. The oldest granites are dated at 3.8 billion years. To form these oldest granites, which represent parts of the oldest continent, subduction must have operated. There was no subduction, no stagnant lid, and if there was subduction, most probably there was some sort of plate tectonic process operated. This subduction would not have been exactly the same as what we see today. The oceanic crust would have been thicker, it would have been hotter, it would probably be more hydrated than nowadays because the hydration zone at the top of the crust was different. The thicker crust would not have bent so easily, so probably the subducting slabs were shallower than nowadays. Perhaps there was no mantle wedge. So the subduction process would have been different in detail, but the basic process would have operated. Subduction is the only process that can take water and basaltic material to depths where the water enters, water enters the hot mantle wedge that can cause melting to form the granitoids. So in the second part of the talk, the last part, the shorter part, I'm going to talk about the rate at which these processes operated, the tempo of the growth of continental crust, or controlled, driven by subduction, but subduction that did not operate continuously. And here the main source of evidence is various records, various compilations of the uranium-lead zircon ages of zircons. Uranium-lead ages of zircons. And when we plot up these data, zircons either from granitoids, shown in red, or from various zircons, detrital zircons in rivers, we see the distribution is not uniform. There are definite peaks and troughs between these peaks. In most compilations, this peak at 2.7 billion years is very obvious. Another one at 1.8 is very obvious. Less obvious in most compilations, but still present at two other peaks at 2.5 and 2.1 billion years. Before there don't seem to be obvious peaks. And after, there are also a number of peaks. But I'm going to focus on these, the peaks towards the end of the Archean and through to the Proterozoic. Now, again, there are two schools of thought concerning the origin of these peaks. One, which I call the creationist interpretation, is that the peaks grow during periods of enhanced, accelerated mantle activity. So Stein and Hoffman talked about MOMO, mantle overturn major orogeny. The idea was that there were episodes in which there was major mantle upwelling, which triggered accelerated return of material to the mantle. And this upwelling led to periods of accelerated subduction, accelerated real continent growth. The alternative explanation, advocated by Chris Hawksworth, Dweem and others, Peter Cowan, is that the peaks represent times of enhanced preservation of continental crust, typically during the assembly of supercontinents. So in this preservation theory, Hawksworth, Coward, Dweem, Condi, and so on, instead of having the present situation, as shown in this diagram, in a modern subduction setting, the rate of crustal growth, the rate at which material is extracted from the mantle to become part of the continental crust, is about the same as the rate at which crustal material is returned to the mantle, either by subduction of sediments or tectonic erosion at the base of the crust. So under these sort of circumstances, during operation of a normal subduction zone, there's no net continent growth. This is different during periods of continent-continent collision, when the interiors of the continents are protected from the return cycle. So even though material is being added to the crust, no material is being returned to the crust. So they say during the assembly of supercontinents, there were periods of enhanced preservation of continental material. Presented as an argument for this interpretation is what is shown here. We see peaks, zircon peaks, and here one estimation of the periods of assembly of supercontinents, which have different names, Muna, Rodinia, and so on. The problem with this type of argument is that the correlation with supercontinents, in fact, is very shaky. Is yet another compilation of the ages of the zircons, 2.7, 2.5, a little 2.1, 1.8. These supercontinents certainly existed, but there's no real evidence of any supercontinents that formed in the late Archean and early Proterozoic. Here's another representation from Witowlika, in which we have time here. And this red curve represents growth of the continental crust with peaks here and here and here. And I've shown these peaks here, 1.9, 2.1, 2.5, 2.7. There might be a reasonable correlation for these peaks with supercontinent formation, but in the Archean and the late Proterozoic, the correlation doesn't work. What we see instead is a correlation with major volcanic episodes, periods of enhanced eruption of volcanic rocks in the greenstone belts of the Archean and the Proterozoic. So there seems to be a correlation between these peaks of continental crust formation and major mantle episodes, as advocated by Stein and Hoffman. So what are these major mantle episodes? Do we have any evidence that periodically through Earth history, the mantle convected more vigorously? And we do see some evidence, but specifically when we look at the oceanic plateaus. We can also look at the continental large igneous provinces, but the oceanic plateaus are more interesting. Here we show a map with the Ontong Java Oceanic Plateau, another one, Manihiki, another one, Hikurangi, which formed all at the same time, around, give or take a few tens of millions of years, 120 million years ago. An immense amount of basaltic material was produced by melting in the mantle, probably by a mantle plume, and this material rose to the surface. In 2005, Coffin and Eldenholm did a very interesting calculation. They calculated the volume or the mass of this oceanic plateau. They assumed 10% melting, and they calculated the volume of the mantle source, the material in the mantle that must have melted to form the basalts in the Ontong Java Plateau. And they found that 5% of the entire volume of the upper mantle was represented by the source, the Ontong Java Plateau. If we add this one and this one as well, we find that the source of the basalts in these oceanic plateaus represents about 10% of the total volume of the upper mantle. In other words, at this time, material that was once in the lower mantle moved into the upper mantle where it underwent partial melting to produce the oceanic plateau. If such a large volume of material moved from the lower mantle to the upper mantle, there must have been return flow. And certainly today, the most reasonable method of returning material from the lower mantle, from the surface, back into the lower mantle is by subduction. So in this interpretation, the peaks that we see at 2.7, 2.5, and so on, are driven by episodes of enhanced mantle convection, which lead in turn to episodes of enhanced subduction, which produces periods of accelerated growth of the continental crust. So, conclusions. Sagduction cannot produce granite. The continental crust and the Archean, like now, form mainly in subduction zones. Subduction started early in the Archean. Subduction and crust formation was episodic, certainly through the Archean and the Episodic. Was episodic, particularly in the period 2.7 to 1.8, triggered by mantle-driven plume events. And that's it. Thanks very much.
Thank you so much, Nick. That was really, really interesting. We have time for questions from the floor, but also from the folks on Zoom.
So I won't ask you to do the poll again.
So do we have any questions from the room? Let's start with the race and then we'll come to you, Lou.
At the mantle group. How fast do we produce this melt? And is it enough, that rate, is it high enough, strong enough to produce that great amount of outpouring of the magma which we see, let's say, in the east, so because with the age which I see now, it's very narrow period of time that they erupt. So it looks very fast. And my kind of feeling that this does not match the melting rate in the fluids. What do you think about it?
Nick, can we just repeat the question?
Okay, the question is, if you're talking about large igneous provinces.
Yeah.
We know in large igneous provinces that a large amount of basalt is produced, erupts in a short period of time. And the question is whether this is consistent with the rate at which we would expect basaltic melt to be extracted from the source. Yes.
They produce.
Produce. Well, no, it's produce and extraction are two different processes, in fact, because I was just doing some calculations with Pedro Waterman about this in the connection of komatiites, but there's a different issue. But what we calculated then is the rate of melt migration within a rising plume compared with the rate of plume ascent. And it's fairly clear that the melt, under normal circumstances, the melt migrates much quicker than the plume ascents. Because if you want to try to answer your question, you would have to consider first the rate of plume ascent, which is probably not fast, not as fast as is needed. But the melt is going to move much faster than the plume, which would mean that it would rise quickly to the surface. And I think if you follow that sort of reasoning, you can come up with numbers that are consistent with the volume of basalts and the rate at which they erupted. It's a good question. But
Okay, any more questions from the room? Yes, Ben, would you mind coming up, Ben, just so we don't have to repeat the...
Well, it's a short question.
Okay. Okay.
Why don't we find Archean ophiolites then? You make this argument that you've got oceanic crust, potentially the temperature of the mantle are not high. Why don't we get Archean ophiolites?
Well, I think what is an ophiolite? You're scraping off the upper part of a crust, which is 6 to 9 kilometers thick. Occasionally, you will see the basalt, the sheeted dikes, the cumulates, and part of the underlying mantle. But if the mantle was, let's say it was 150 degrees hotter, there's a direct relationship between the temperature of the mantle and the thickness of oceanic crust. And I think it's reasonable to expect that the oceanic crust was maybe 20 kilometers thick. And in that case, it's very unlikely. We're not even sure if there were sheeted dikes because it's more like a fast-spreading ridge, modern ridge, where you don't really see the dikes. So you just don't see the elements of a oceanic crust abducted, preserved on the continents. That's why you don't see ophiolites. Another interesting question is, do we ever see any Archean mid-ocean ridge basalts? I'm not sure. I think most of the basalts and greenstone belts form part of oceanic plateaus, plume-related.
Anthony, and then we'll go to the questions on the Zoom.
I argue against the Sagduction. I mean, the natural result of plate tectonics on the surface is one of them is the sedimentary basement. So Sagduction people, with their still within their model, have dust belts, back off bases, and all of that sort of stuff. Or what is the argument for? How would those form in that situation?
Part of the arguments for a late start of plate tectonics does concern back arc based passive margins, sedimentary basins, and so on. I don't think that argument is correct for two reasons. First, if the mantle was hotter, it was drier, which means a large proportion of the water on Earth was present in the oceans. The oceans were deeper. There was less continental crust around. So certainly throughout most of the Archean, there's probably very little land. There's a little bit around Barberton. There you get these 3.2 million year old sediments, right, Carl? Which probably, there was erosion of emerged continents, but that was rare. I think the absence of these features is more to do with competing processes, dropping of sea level, gradual growth of continental crust, so there's more and more continental crust, appearance of emerging land, and so on. Nothing to do with the overall geodynamic process.
Okay, let's move on then to Sue. Sue, come through. You should be able to unmute.
Okay. Hi, Nick. It's Sue Webb here. Sorry, I'm home with COVID.
That's something.
Yeah, sorry about that. I wanted to ask, what evidence would be convincing in terms of deep crustal seismic? I mean, we draw all these cross sections, these comics through the crust, but we rarely base them on seismic evidence. And I'd like to, really ask, when are we going to start bringing the seismic data into this, and what evidence from the seismic would be convincing for either model?
Okay, no, it's a good question. Sue, I think you know that, for example, in lithoprobe, which is the Canadian deep seismic profile, they found reflectors that seem to go from the crust, reflectors near with shallow dips going from the crust into the mantle. And these were interpreted as relict subduction zones. No, I don't believe that. I find that hard to believe. But what else would you look for? One other thing which I think is important is in the seismic sections in the Archean areas, it seems that most of the crust has a granitic composition, which is important. It reinforces the idea that the continental crust is mainly granitoid. This is important because yet another argument put forward by the advocates of Archean, of stagnant lid, were geochemical arguments which seem to indicate that the continents were more mafic in the Archean. The composition of sedimentary rocks, they seem to have a higher content of magnesium, nickel, and so on. So this leads to the argument that the crust in the Archean was more mafic, and this leads, I'm not sure why, to the statement that this indicates the geodynamic process was different. I don't accept that. And just going back to what I mentioned before, the Archean crust was mainly granitic, and I think the geochemical arguments are incorrect. Does that sort of answer your question?
Yeah, we've got a lot of seismic data here, and also other geophysical methods that would, indicate what's going on in the deepest crust and might actually preserve evidence of what was happening then. Anyways, thanks. Yeah, great talk.
Just quickly, the real problem with seismic evidence, it shows what the crust looks like now, and it doesn't tell us much about what it looked like when it formed. There's certainly been the crust is processed, lower crust, upper crust, have different compositions, so not a movement. So what we see in the surveys, is only a snapshot of today's situation.
Thank you, Sue. Let's go to Lou and then to Wolfgang.
Okay, I'm here. Nick, I really wanted to be with you in that room today, but due to the outbreak of COVID, and I have to go to my daughter's house to live for 10 days, I have no transport to get in there. So very sorry about that. I don't really have a question, but I have a comment that was inspired by a talk, a couple of talks given not too long ago by Lawrence Robb, who was talking about Barberton. And he's a big proponent of Sagduction for the Archean. And I guess his reasoning is that, look, there's a lot of komatiites out there and basalt too. These are dense rocks, and they're just not going to stick around. They're going to be gravitationally unstable and sag or sink back into the mantle. And this is his argument. And when I questioned him about this, I told him, of course, that I don't believe any of that crap about Sagduction. And he said, yeah, but surely you have to accept the fact that these are dense rocks and they're going to want to sink. And I said, and he challenged me to disagree with this. And I said, I don't disagree that they're not dense, for God's sake, but here's an example, not too far away from where we're all standing right here, the Bushveld complex, which is the biggest damn dense piece of dense rock that I know of in the solar system. and that didn't sagduct. So, you know, how do you explain that? He said, well, fair enough. But he didn't defend his arguments. And a lot of these guys who favor sagduction, when you question them with observations, measurements of all different kinds, they say, yeah, that's a good point, but I'm not prepared to change my views. So that's all I got to say, Nick.
Okay,
you can respond if you want to.
It raises an interesting point. So I've just put up this slide. It's from the Pilbara, and you see this basin and dome and basin geometry, which certainly exists. And here we're seeing evidence of some sort of vertical movement with the granitoid domes moving up and the subduction and the greenstones moving down. That certainly happened, but that was part of the process that happened within the crust. And I don't think this should be confused with the process that formed the crust. They're quite different. And this brings me back to what Sue talked about. If most of the crust, the Archean crust in Barton and elsewhere, has a granitoid composition, and it seems, correct me if I'm wrong, Sue, that the greenstone belts seem to be preserved slivers in the uppermost part of the crust, in the more rigid upper part of the crust, and they're not present. They're relatively few mafic rocks deeper in the Archean crust. So what I think has happened is that probably a lot of the dense material here would have moved down because it's denser, and would have moved through the crust to be lost to the mantle. No problem with that. That happened, most probably, but it's not a crust forming process.
Okay, and then Wolfgang will end off with you. You should be able to unmute now.
Yeah, thanks, Grant. Hello, Nick. Thanks for the good talk, interesting talk. First, quick question to Nick, which he kind of answered already a moment ago, because I was reminded of a paper that Nick published about 10 years ago on anorthosites, where he proposed that these things are leftovers.
Grant is standing next to
These things are leftovers with their ultramafic components being sagging down into the mantle. So a moment ago, you said these things happen in the crust, within the crust. So, you know, this is a little bit of an analogy to the sagduction thing, and I guess you should perhaps explain to us what's the difference there. But before you do so, quick comment on Lou's discussion with Lawrence Robb. Lawrence, it seems, believes in or argues that dense material should go back into the mantle. Lou used the Bushveld complex to argue against that. I just would like to point out that the Bushveld complex, while it is the world's largest mafic ultramafic massif, the entire center of it is not exposed, and one could argue that the entire center of it has, sinking back into the mantle. Although I am aware that Sue, of course, has a different model for this lack of Bushveld in the center.
It's a little bit of flexure, Wolf. It's not sagging. It's not sagducting. It is sagging, but it's due to flexure. Sue can explain.
Yeah. There's evidence both from the kimberlite and from the gravity data that it would still have mafic material present in the center.
No, but yeah, getting back to the main point, we're talking about growth of the continental crust. That's what I'm putting the emphasis on. And for me, for a petrologist, a geochemist, growth of the continental crust is, in one step or two steps, extraction of granitic material from the mantle into the crust. And I think this happens with subduction. If cromatiite, which is at the surface, ultramafic material, goes back down to the mantle, well, yeah, so what? That is taking mafic material and surface back into the mantle, and that has it's a process which is quite different from this revert process in the other direction, extraction of granite from the mantle.
Okay, well, this is a great discussion, and I see two more hands. So if you don't mind, Nick, can we continue it for a little bit longer? Kenny, would you like to come through, and then Spike?
Just a quick question. On the first question answered, you referred to, with a little bit of doubt as to the mechanism of mantle plumes. Quite fitting the mechanism of supply of such a large volume. isn't it time there should be a bigger question mark against that mechanism at this point in time?
What, the question mark over the existence of plumes?
No, well, of them being, they don't quite fit in as I say, in the supply of such a large volume of material. If rather than trying to make it fit, wouldn't it be time to question whether that is actually, explaining it all?
Henny, do you mean in terms of the volume of material being unreasonable?
Yes. Yeah.
The volume of the source, or the volume of melt, or the volume of the source?
The volume of the source.
Of the source. I don't quite know how to. This. Get back to that.
Go for it.
Okay, well, now I'm just showing on Java again. It's true, if you do the calculation of Coppen and Elmholm, which is reasonable, it does require that a very large volume of mantle material came very close to the surface. It has to get within about 150 kilometers of the surface to melt. And this requires a pretty rapid flux of a lot of material close to the surface. But I don't see any way around this. I don't think that any of the non-plume mechanisms, incubation or something else, provides a better argument of this. The best way of taking a lot of material from deep, where it is hot, close to the surface, is in a plume. I don't see any alternative to that.
Okay, thanks, Henny. And then we'll end off, really this time, with Spike McCarthy. Spike, you should be able to unmute.
Okay, you got me.
Yeah, we got
just a couple of things that have come to mind. I don't work in this field and not remotely connected with it, but I remember there was a time when Martin de Wit raised this issue of the great thicknesses of komatiite we find in the Onverwacht. And 20, 30, 40 kilometers of uninterrupted komatiite eruptions. And he proposed that the whole thing was just masses of duplications of faults, that the Viljoen's mapping was just missing out on all the structure. And there was a big argument with Don Lowe and everybody. And I'm not sure how that was ever resolved. But I suspect that people still imagine these great thicknesses of komatiite. So they would have formed the early crust. And if you compare it with modern continental crust, which is about 7 kilometers, those things are amazing. Those Archean komatiite sequences. And they're full of pillars, so we know they're submarine and whatnot. And then coupled with that is this whole question of these batholiths. You were showing what McGregor called the gregarious batholiths, which are these diaperic-like batholiths. So you easily imagine, and I imagine this is what Lawrence Robb is thinking as well, that you've got this enormously thick crust, which is slowly sagging into the mantle, and the mantle is much hotter than it is today, because the melting temperature of komatiite we know is 1600 degrees or something. So your mantle temperatures are up at that. It's conceivable that those things are starting to melt and generating these the TTG suite, which is coming up in these diaperic structures, which is characteristic of you see them in Australia, you see them in South Africa, Zimbabwe. They're part of the story, and they fit so nicely with a Sagduction model. So I don't know. We're just looking at it, from the outside. To me, that's much more appealing. When you can't see the typical features of subduction, like people have mentioned, you want the ophiolites, you want indications of metamorphism. Here we've just got these slivers of continent that just slide up next to each other, and there's no metamorphic boundaries between them.
Mm.
So we're looking at it, it's a completely different kind of world. This is not a world of subduction and merging, subducting slabs and colliding continents. It doesn't look like that.
Oh, I think
that's just my view.
I still think it does. No, a couple of points. Carl, what is the metamorphic grade in the lower Marty formation? It's not that high, is it? It's touching. A little bit like facies, clinches. Yeah, this thick, you cannot have a 20-kilometer thick pile of basalt. There must have been some repetition or some sort of imbrication of the different volcanic units. The volcanic pile was never that thick. But just going on, again, you talked about sagging, dripping of material down into the mantle as a mechanism of producing granitoid. And this is the point I was trying to make. I brought up this diagram again. If mafic material drips down, the water that will be released by dehydration, the water that is essential to form granitic magnets, the water that is essential to produce the geochemical subduction signature seen in granitoids, does not move into overlying hot mantle wedge, which can melt. It moves up into colder rocks. Now, adding water to cold rocks is not a good mechanism to do anything except a bit of hydrothermal alteration, but it does not produce granitic magnets.
Okay, I think we'll end it there, mainly because I actually have to go teach. But Nick is going to be around for another 2 hours. He'll be sitting in my office, so anyone who wants to come chat with him, please feel free. There's coffee there and whatever you like. So please feel free to come chat after this. And everyone on Zoom, thank you for joining us. We have a talk on Thursday, so don't forget about the talk on Thursday from a PhD student here, Mbato Mpeloko, who will be speaking about the Zebediela nickel copper PGE project. So we hope that you'll all join us. And thanks once again, Nick, for a fantastic talk and a great discussion.
Thank you.